Hi everyone, welcome back to Math 111. This is Scott. Let's get started. Today what we're going to talk about is section 5.5, where we will be discussing the zeros of polynomial functions. Alright. So I want to start by just listing some of the things that we're going to be using here, and then we'll start going through examples of them. So I just want to get a lot of the specific theorems and such that we'll be making use of out of the way. So first off, there is what is called the remainder theorem. So first, what this is, second, what we use it for. So if f of x is a polynomial, and we divide it, for example, by synthetic division, for example, by x minus k, then the remainder will be f of k. So in other words, if we divide it by something of this form, where it's x minus a number, then the remainder will be what you would get if you had plugged that number in. So in other words, it would be evaluating it. So a consequence of this is if the remainder is 0, then k is a 0 of f of x. In other words, it's a root or an x-intercept. Okay, so that's one way of checking whether something is a 0 of a function. Now, if it is a 0, then what that leads us to is what is called the factor theorem. Factor theorem. If k is a 0 of f of x, then x minus k is a factor of f of x. And what that would mean is that we could then, after doing the synthetic division, look at the quotient, and that'll be the other factor. The quotient will be the other factor. Now, we could actually take that quotient, which will be a new polynomial, and we can in fact even repeat the process that we just did to find out if k was a factor of the quotient as well, and that'll mean it has higher multiplicity. So if k is still a factor, of the quotient, then it has higher multiplicity. As a 0. So we will then repeat the process of synthetic division to see how many times k actually appears as a factor. Okay, and now the last in this little sequence of theorems, and that is going to be what is called the rational zero theorem. Rational zero theorem, and what this says is that if we have any polynomial with integer, as in whole number, coefficients, then the only candidates for rational, in other words fraction, zeros, that means, in other words, fractions, not expressions with square roots. So that's the opposite. The other situation, if it's not a rational zero, it's going to be something that involves square roots that you get from the quadratic formula. Not expressions with square roots. Will be of the form, so they're fractions, so we know it's going to be something divided by something, and the something divided by something here will look like this. So it's going to be a fraction p over q. It'll be of the form, and then we can say p over q, where p is a factor of the constant term, and q is a factor of the leading coefficient. Okay, now just put that all out there, and now let's discuss how we will actually make use of this. So using all these theorems. So using these theorems. Here's going to be our process. So our goal is going to be to find the zeros of a polynomial. Find all the zeros of a polynomial. That's the goal. And here's the approach. Use the rational zero theorem to make a list of possible rational zeros. Then try each one by synthetic division f of x divided by x minus k. If the remainder isn't 0, discard that candidate. If it is, and if it is 0, then look at the quotient and then try to factor it if you can do so. If you can't, then try just repeating that synthetic division again with possibly the same factor. So if it is 0, look at the quotient and try to factor. Use synthetic division again. If appropriate. Once the quotient is quadratic, we can also use the quadratic formula to solve. Alright, well, that's enough talking about that. Let's just see what we can actually accomplish here. So now let's try some examples. So we'll start off simple, just trying to remind ourselves really how synthetic division works more than anything. So as an example, let's say we want to just find the remainder. So for example, let's take 3x cubed minus 2x squared plus x minus 1 divided by, and then just something like x plus 1. Okay, so this means then we're talking about x minus k, where k is minus 1. So k is negative 1. Okay, so then to use synthetic division, what that's going to look like is we will now put that number there, the k, up here, minus 1, and then here go the coefficients, 3, negative 2, 1, negative 1. Now the first coefficient of the quotient just comes straight on down and it's just a 3. And now we just do 3 times the negative 1 in order to produce what goes over here. So it's going to be negative 3. Then we just add those and we get a negative 5. Then we just multiply this times that, and that's what goes over here, so it's going to be a 5. Then we add those and we get a 6. And then we multiply those and we get a negative 6. We add those, we get a negative 7, And that is the remainder, which means that if we were to plug -1 into this polynomial, we should actually get a -7. As a quick check, what would happen if we plug -1 in here? We would get -3 minus, that would become +1, so -2, so that would be -5, -1, -1 more. So -7 is what we would get if we plugged in -1 into the original polynomial. So the remainder is -7, which means that that this is not a factor of that. The remainder would have had to be 0 for this to be a factor. Okay. So there's that. Now, so that was just a reminder of how synthetic division even works. And now let's let's actually try to use this to find the zeros of the following. So let's say find the real zeros of the following. By using the factor theorem. With the given factor. Alright, so let's try the polynomial 2x cubed minus x squared minus 16x plus 15, and we'll be given the factor x plus 3. Okay, so then this is, if this is going to be x minus k, that implies that k is -3. So then the way synthetic division will work, we put that -3 up here, and we put 2, -1, -16, 15. Now for the first part of the quotient, we just bring down the first coefficient, and that's so that's going to be 2. Now 2 times -3 is going to be -6, and then we add those to make a -7. -7 times -3 is going to be +21. Then we add those, and that's going to give us a +5. 5 times -3 is going to be a -15. We put that here, we add those, we get the 0, and this is where the remainder is. So the remainder is 0, which it should have been if this really was a factor of the polynomial in question. So we have a remainder of 0. And what that means then is that 2x cubed minus x squared minus 16x plus 15, we know that this is equal to x plus 3 is one of the factors of it, and then the other factor we get by just taking the quotient here. So this is going to be the x squared term, this is going to be the x term, this is going to be the constant term, and then this was of course the remainder. So it's going to be 2x squared minus 7x plus 5. Now, when it comes to this, if we want to factor this, we can do it by a couple different means. We can do it by grouping. We can do it by what they call the AC method, or if you're really feeling like just going for the nuclear option, you could just do the quadratic formula as well. Now, there's no reason why we have to resort to any fancy new things to factor this. We can use old, time-honored factoring techniques, such as just unfoiling it. So we don't actually need to use any more synthetic division or anything like that, although such things could be possible. We can just do classic stuff. So I know that if the two things are going to have to multiply together to make 2x squared, it's going to be a 2x and an x. Now over here I'm going to have to put two things that multiply together to make positive 5. But my middle terms are going to have to add up to a negative 7. So I know they're going to have to be negative and negative. And furthermore, I know that they're going to have to be a 5 and a 1. It's just a matter of balancing them out, figuring out which one goes where. Well, I need the middle two terms to add up to a negative 7. And I can tell that if I have a 5 here, then that would make 1 times, so that would make 2 times 5, and then that would make, and then minus 1. So that would be negative 11. That's not going to work. So the 5 can't be there. It has to be over here. And that's going to make a 1 over here, and a 5 over here. And then if we look at that, that's going to be, it's going to be now 2x squared, check. Minus 2x, minus 5x, check. Plus 5, check. So then, what that gives us is x plus 3 equals 0, means x equals negative 3. 2x minus 5 equals 0, which means that 2x equals 5, which means x equals 5 halves. And then x minus 1 equals 0, which means x equals 1. So that gives us our real zeros of x equals negative 3, 1, and 5 halves, just listing them in order from least to greatest. There's no reason why you have to be, why you have to put them in any particular order instead of another, but just to have some order, we'll just go least to greatest. So there's that. Now let's try this again one more time with a factor, with a polynomial and factor of x cubed minus x squared minus 3x plus 2, and then x minus 2. So this is going to be one of the factors of that, supposedly. But if we want to be sure, we have to do the synthetic division anyway. So x minus k is that, which means k equals 2. All right. So then the synthetic division, we're going to put the 2 over here, and then we're going to have 1 minus 3 and 2, just the coefficients of this. If there were any missing terms, we would have put a 0 in there. Now down comes the first one. Now we do this times this to make the one that goes over here, and we add those. That's going to make another 1. We do that, put them over here. We add those. That's going to make a negative 1. And then negative 1 times 2 is negative 2. And that's going to make a 0 right here, which sure enough is what we needed. So the remainder is 0. So what that means is that the x cubed minus x squared minus 3x plus 2 is the same as x minus 2 times x squared plus x minus 1. Now, we're not going to be able to factor this, you can tell, because of the fact that it's got two numbers that multiply together to make negative 1, add together to make positive 1, hard sell. So, what that means is we are going to need to take it in pieces. So, first off, the x minus 2 equals 0 will lead us to x equals 2. Nothing wrong there. Over here, if I want the zeros of this, I'm going to need x squared plus x minus 1 equals 0. If I can't factor it, then there's not really much else for me to do besides the quadratic formula with a equals 1, b equals 1, c equals negative 1, and then x equals, it's going to be negative b plus minus square root of b squared is 1 minus 4 times a times c, all divided by 2a. It's going to be negative 1 plus minus, and then over here that's going to be positive. It's going to be square root of 5 over 2. So what that means is we're going to have x equals 2, x equals negative 1 plus the square root of 5 over 2, and then x equals negative 1 minus the square root of 5 divided by 2. Sometimes you will see these two types of roots rewritten as negative 1/2 plus 1/2 square root of 5, where you just basically distribute the 2 into the two pieces. Doesn't really matter, it's just another way of writing it that sometimes makes it a little bit easier to see that we have, or to see exactly what sort of values these will be, and sometimes you will give an approximate answer if this is something where you need something that is actually of relevance to somebody who wants to measure something or cut something or do something like this. Okay, so this is how this will go. Now, the next example, we're going to use the rational zero theorem to get all the real zeros. To get all real zeros. So what that means is we are going to start by finding out what possible rational solutions there are, and then we're going to try to get to one. As soon as we can get one, then we'll be able to factor it out, and then we'll be able to proceed from there. Okay, so here is our first example. 3x cubed plus 4x squared minus 7x plus 2 equals 0. Alright, so here is the leading coefficient. Here is the constant term. So all possible candidates for a rational, as in a fractional root, one that doesn't require the use of the quadratic formula, something that instead can be done by factoring, all the possible candidates are going to come from factors of this divided by factors of that. So let's just think about what the factors of the constant term are. So the constant term is 2, so we can break it down into 1 plus or minus and 2 plus or minus. So factors of the leading coefficient are going to be, again, things that go into 3, so it's going to be 1 plus or minus 1, and 3 plus or minus 3. So what that means is we have the ability to mix and match any one of these over any one of these. So candidates here. The candidates are going to be 1 over 1, 1 over 3, 2 over 1, and 2 over 3, and in all cases plus or minus. Plus minus, plus minus, plus minus, plus minus. So in other words, plus minus 1, plus minus 1/3, plus minus 2, plus minus 2/3. Okay, well, now when it comes to doing this, it can be a little bit tedious to try everything, and since we are just trying to go basically until we get a hit, we'll just go with the, we'll just start with whatever is easiest. So we can start with the 1 or the -1, or the 2 and the -2 to see if any of those work. We would ideally like to get our to find our solution as quickly as possible. So let's just try them. Let's just try k equals 1. So this means we're plugging in. So this means we're going to look for a factor of x minus 1. Okay. Well, that means we're looking at a 1. And basically, I'm just trying the easiest one I can find. 3, 4, -7, and 2. I want to get a hit as quickly as I can. So put in 3, multiply, that makes a 3, add, that makes a 7, multiply, put a 7, that makes a 7, and then add, that makes a 0, multiply, that makes a 0, that makes a 2. So, nope. Okay. So be it. Alright, well how about k equals -1? So that means we're looking at the factor x plus 1. So -1, 3, 4, -7, 2. So down comes a 3, and then 3 times -1 is -3. Add those, and you get a 1. Multiply those, you get a -1. Add these, you get a -8. Multiply, you get an 8. Add those, you get a 10. And so we have a remainder of 10, and that's a no. Okay. Let's try k equals 2, which means a factor of x minus 2. So then that means we're going to have 2, and we're going to have 3, 4, -7, and 2. And down comes the first one for the first term. And now 2 times 3 is 6. Add those, you get 10. 2 times 10 is 20. Add those, you get 13. 2 times 13 is 26. I can already see this one is not going to pan out. So remainder 28. So that's a no. Okay. How about k equals -2? So it's going to make an x plus 2. And here we try. So 3, 4, -7, and 2. Down comes a 3. That's going to make a -6 when we multiply. Then we add, and that makes a -2. Then we multiply, that makes a +4. Then we add, that makes a -3. Then we multiply, and that makes a 6. And we add, that makes an 8. And it looks bad again. Remainder of 8. Okay, so we tried these ones first because they were the easiest. Unfortunately, they didn't pan out. Oh well, these things happen. So now let's try with the 1/3. So k equals 1/3. So that means x minus 1/3 would be the factor that we're talking about here. Alright, so we've got a 1/3, and that's gonna make, and then that maybe does, maybe doesn't, go into 3, 4, -7, and 2. So down comes a 3. Multiply the 3 times the 1/3. That's going to make a 1. Add those. That's going to make a 5. Then 5 times 1/3 is going to make a 5/3. 5/3 minus 7. So that's 2 1/3 and -7. So it's going to be, so 7 is 21 thirds. It's going to be -16 thirds. And then multiply that with that, and I can already tell. It's not going to be 0. But just for the sake of argument here, it's going to be 18/9 minus 16/9 is going to be 2/9. So a remainder of 2/9, which is not 0, so no. Alright, well, what about if k equals a -1/3, which would mean a factor of x plus 1/3? Well, here we go. -1/3 going into 3, 4, -7, 2. Good. A lot of good synthetic division practice here. So down comes a 3. So that's a -7. Okay, and then that makes a -1, and then multiply those. That makes, add those. That makes a 3. Then multiply. That makes a -1. And then we add those. That makes a -8, so close. And then we multiply those, and that's going to make an 8/3, and we know that that remainder is not going to be 0. But just for the sake of argument, it's going to be 6/3 plus 8/3 is 14/3. And so, no. Nope, not that one either. Okay. Well then, what if k equals 2/3? That would be then the factor x minus 2/3. Let's see how that works out. So, 2/3. Starting to scrape the bottom of the barrel on our possible factors here. Better get a hit soon, otherwise we give up. So 3 comes down, and multiply 3 times 2/3, it's going to make a 2. Add those, it's going to make a 6. Multiply those, it's going to make 4. Add those, it's going to make a -3. Multiply those, it's going to make a -2. Add those, it's going to make a 0, and we finally got our hit. So yes, we finally got it. So that means that our original polynomial 3x cubed plus 4x squared minus 7x plus 2 is equal to, and what we've got here is x minus 2/3 as one factor, and then the other factor would be 3x squared. So remember, this is x squared, this is x, this is constant. It's going to be 3x squared plus 6x minus 3. Now here, we can actually pull out a common factor of 3. We have an x squared plus 2x minus 1. And now we can see, so we already knew that one factor was, that gave x equals 2/3 as one of the zeros. But over here, we can see that this is not going to, this one is not going to be factorable. So therefore, we're going to have to use the quadratic formula. So a equals 1, b equals 2, c equals -1, and we'll get x equals -2 plus minus square root of 4 minus 4ac, so it's going to be plus 4 divided by 2a, which is going to be 2. Now over here, what we've got is negative 2 plus minus, and it's going to be the square root of 8 over 2. But we can actually simplify that a little bit. So square root of 8. But now let's see how we can simplify this. So x equals negative 2 plus minus square root of 8 over 2. So this is what we're going to try to simplify. But 8, we can break that up into 2 times 4. So it's going to be negative 2 plus minus square root of 4, square root of 2. Over 2. But actually, I know what the square root of 4 is. It's going to be negative 2 plus minus 2 root 2 divided by 2, which we can then factor out the 2 from the two pieces of the top there. So it's going to be negative 1 plus minus square root of 2 all divided by 2. So let's cancel. So then that gives us the zeros of x equals 2/3, and then we have a pair, negative 1 plus square root of 2, and negative 1 minus square root of 2. The two pieces of this when those all cancel out. Okay, so that one, it took us a lot of tries before we ended up finding the right one. Sometimes, though, that's just the way it's going to be. Other times, we might get lucky. Let's try another example here. 2x cubed minus 3x squared minus 3x minus 5 equals 0. So again, the two things that we're looking at are the leading coefficient and the constant term. So the factors of negative 5, that's going to be plus minus 1 plus minus 5. Factors of 2, it's going to be possibly plus minus 1 plus minus 2. So then the candidates are going to be 1 over 1 plus minus, and 1 over 2 plus minus, and 5 over 1 plus minus, and 5 over 2 plus minus. Now, let's say I had a burst of sudden inspiration, and I decide I'm going to try this one first. So, by the way, these are just really plus minus 1, plus minus 1/2, plus minus 5, and then plus minus 5/2. So we could go through the whole rigmarole that we did last time and try all of them from the beginning to the end, but just to shake things up and for reasons of let's say divine inspiration, I'm going to start with that one first. So we can start with any of them, and let's just say k equals 5/2. So that would be a factor x minus 5/2. So what that's going to look like is 5 over 2, and then we're going to have here 2, negative 3, negative 3, negative 5. We're looking for a remainder of 0, remainder of 0. So down comes a 2, multiply those, and that's going to make a 5. Add those, that's going to make a 2. And then we multiply these, that's going to make a 5. We add those, we add those, it's going to make a 2. We multiply those, it's going to make a 5. We add those, it's going to make a 0, and we've got a bingo. So this is a yes. Which means then we're able to move to phase 2. So 2x cubed minus 3x squared minus 3x minus 5 is the same thing as x minus 5 over 2 times. And that's going to be right here, x squared. This is going to be the x, this is going to be the constant. So it's going to be times 2x squared plus 2x plus 2. But that means I can factor the 2 out of those. It's going to be x minus 5 halves times 2 times x plus 2. Sorry, x squared plus x plus 1. Alright, there we go. So now x minus 5 halves equals 0. That means that x equals 5 halves. X squared plus x plus 1 equals 0. If that's what we're dealing with, then I need to factor it if I can. Here I can't. So therefore, the quadratic formula. A equals 1, b equals 1, c equals 1. And that's going to mean x equals negative 1 plus minus the square root of 1 minus 4ac all divided by 2a, which is going to be negative 1 plus minus square root of negative 3. So this is non-real, not a real number. Okay, so then what that means is the zeros, the only real zeros, are x equals 5 halves, and that's the only one. And now the last one of these examples, we're gonna up the difficulty level slightly with a higher degree. Gonna make it a degree 4. So let's go with the last of these, C, which is going to be dealing with 2x to the 4th plus x cubed minus 24 x squared plus 20x plus 16 equals 0. Okay, so there and there are what we're looking at. So let's go factors of 16. Well, the things that go into 16 are plus minus 1, plus minus 2, plus minus 4, plus minus 8, or plus minus 16. And the factors of 2, that's much easier. It's just going to be plus minus 1, plus minus 2. So that gives us as candidates 1 over 1 plus minus 1 over 2 plus minus 2 over 1 plus minus 2 over 2 plus minus. So notice those are the same. 4 over 1 plus minus 4 over 2 plus minus. But if we reduce that, that's the same as that one. We've got 8 over 1 plus minus. We've got 8 over 2 plus minus. So notice that's the same as 4 over 1. And then we've got finally 16 over 1 plus minus and 16 over 2 plus minus. But that has a lot of redundancy. So if we simplify it all down, really what we're talking about is plus minus 1 half, plus minus 2, that's just going to be a copy of 1, so that's fine. Plus minus 4, that's going to be just another copy of 2, plus minus 8, That's just going to be another copy of 4, and then plus minus 16. And then that's just going to be another copy of 8. So we've got a lot of redundancy here, so it all boils down to these options, and let's just go ahead and go for it. And we'll just start with let's just start with a 1 and work our way across. So k equals 1, meaning x minus 1 will be the factor that we're talking about here. So it's going to be 1. Hoping to go into 2, 1, negative 24, 20, and 16. Let's go fast. So down comes a 2, multiply, that makes a 2, add makes a 3, multiply makes a 3, add makes a negative 21, multiply makes a negative 21, add makes a negative 1, multiply makes a negative 1, add makes 15. So that's a no. How about if k equals negative 1? Meaning x plus 1, I should say. X plus 1. So it's a negative 1 now. 2, 1, negative 24, positive 20, positive 16. Down comes a 2, no. Multiply makes a negative 2, add makes negative 1, multiply makes a 1, add makes negative 23, multiply makes positive 23, add makes 43, multiply makes negative 43, add does not make 0. So for the record, it's whatever it is, 27, negative 27. Or whatever it is. Not 0. That's the important thing. So, not 0. So it's no. Actually, I guess I was right. Negative 27. And you can use a calculator for some of the drudgery here. Alright, so no. K equals 1/2. Meaning we're talking about x minus 1/2 as the factor. 2, 1, negative 24, 20, 16. Alright, down comes a 2, multiply makes a 1, add those makes a 2, multiply makes a 1, add those makes negative 23, multiply makes negative 23 over 2. That's going to be 40 over 2, so that's going to make 17 over 2. Multiply is going to make 17, add is going to make 33. No. Alright, k equals negative 1/2. X plus 1/2 will be the factor. So negative 1/2. Luckily this is the last fraction one, so if this one doesn't pan out, at least the rest of them are not going to involve any fractions. So down comes a 2, multiply. Times 1, negative 24, 20, 16. So multiply makes a negative 1, add makes a 0, multiply makes a 0, add makes negative 24, multiply makes a positive 12, add makes a 32, multiply makes a negative 16, add makes a 0, bingo! So we got it. So x plus 1/2. So the 2x to the 4th plus x cubed minus 24x squared plus 20x plus 16 is the same as x plus 1/2 times, and then here this is x cubed, x squared, x, and constant. So that's going to be 2x cubed plus no x squared I'll put it in there. Anyway, minus 24x plus 32. Now notice that it has a common factor of 2, so we can actually pull that out. X cubed plus 0x squared minus 12x plus 16. So now essentially I would look at this, and if I can't factor it, which I don't see how to factor something like this, we're going to have to repeat the process for the remaining candidates. So now we're going to be using this. So the next candidate. So we'll use this going forward. So we'll actually do the k equals negative 1/2 again because it might have higher multiplicity is the reason. So that's an x minus 1/2. This is to check if it has higher multiplicity than just 1. So negative 1/2, and now it's going to be 1, 0, negative 12, 16. So now it's going to be a little bit simpler. Down comes a 1, multiply, makes a negative 1/2, add, makes a negative 1/2, multiply, makes a positive 1/4, add, makes, this is negative 48/4, so negative 47/4. Multiply is going to be 47/8, and that's not going to be 0. So, no. Okay, so now we can proceed on with the next of the candidates, which would be k equals 2. So for k equals 2, then that would be a factor of x minus 2. So then here we're going to have 2, we're going to have 1, 0, negative 12, positive 16. Down comes a 1, multiply makes a 2, add makes a 2, multiply makes a 4, add makes a 16, multiply makes a 32, and you'll notice that we are definitely not going to get a 0 here. It's going to be a 48. No. Oops. So the actually withdrawn. Autopilot there. That was supposed to be a negative 12. So when we add these, it's going to make a negative 8. And so here, when we multiply that, that's going to make a negative 16. That's going to make a 0, which is going to make a yes. I thought that sounded wrong. Okay, so yes. So what that means is... that x minus 2 is a factor of that. So x cubed plus 0x squared minus 12x plus 16 is the same as x minus 2 times x. So these are now x squareds, x's, and constants. X squared plus 2x minus 8x. Sorry, minus 8. Now here then, this we can actually see about factoring that. So 4 times 2 will be the thing. So we got x minus 2 times x and x. We're multiplying together to make a negative, so that means one thing's going to be positive, one thing's going to be negative. Has to add together to make positive 2 and multiply together to make negative 8. So that means it's going to be a positive 4 and a negative 2. So what that means is we've actually got all together then, so f of x is equal to x plus 1/2, we already found that, times the 2 times x minus 2 times x plus 4 times x minus 2. So that's, in other words, equal to 2 times x plus 1/2 times x minus 2 squared times x plus 4. So then if I want to separate these all out, I'm going to have x plus 1/2 equals 0, which means x equals negative 1/2, multiplicity 1. Here I'm going to have x minus 2 equals 0, which means x equals 2, but this one has multiplicity 2 because of the square. And over here we're going to have x plus 4 equals 0, which means x equals negative 4, multiplicity 1 because there's no exponent. Alright, so that's the end of those examples. Now, another note that we can make here is that previously, when we have ended up trying to take a square root of a negative, we just gave up. We threw our hands up, we said not defined, we said not real, we just were quitters. But if we allowed square roots of negatives and we call them complex numbers, then we can actually get more solutions. We can get what are called complex solutions. So note, when the quadratic formula produces a square root of negative, we can represent our zeros as complex numbers with I equal square root of negative 1. So for example, let's say we had something like the square root of negative 16. Well, if that had just been 16, we would have known the answer was 4. If it's square root of negative 16, then the I is how we make it negative. If we had something like the square root of negative 8, then that is the same as square root of 8 times I, which is the same as square root of 4, square root of 2 times I, which is the same as 2 root 2I. So now, as an example, let's actually revisit one that we gave up on a little prematurely before. As an example, find all solutions including complex. And for the example, let's take one that we did already, 2x cubed minus 3x squared minus 3x minus 5 equals 0. So from above, we already knew that this factored down. How did it factor? It made, so from above, we already knew that it factored into x minus 5 halves times 2 times x squared plus x plus 1. Now here we got the x equals 5 halves, And from here, we're just going to revisit what we did already. 5 halves. We're going to set that equal to 0, and that's going to have, again, quadratic formula, a equals 1, b equals 1, c equals 1. So x equals -1 plus minus square root of 1 minus 4, all divided by 2, which is going to be x equals -1 plus minus square root of -3 over 2. So that's equal to -1/2. Actually, I should do it. Equals -1 plus square root of 3i, because it was negative, over 2, or -1 minus square root of 3i over 2. So then we have 3 solutions. So then the solutions are x equals 5 halves, -1 plus square root of 3i all divided by 2, and -1 minus square root of 3i all divided by 2. And these can be written as x equals 5 halves. It's a common way of rewriting this, kind of optional, would be -1/2 plus root 3 over 2i, and -1/2 minus root 3 over 2i would be other common ways of writing it. Not necessary, but not forbidden either. Alright, now one more example. Let's take something like this. This is not one from above. Let's go x cubed minus 8x squared plus 25x minus 26 equals 0. So here, if we look at the leading term and the constant term, we are interested in the factors of each. So factors of the constant would be plus minus 1, plus minus 2, plus minus 13, and plus minus 26. As for the other one, as for the factors of the leading, it's just going to be 1, plus minus. So then our candidates are 1 plus or minus, 2 plus or minus, 13 plus or minus, and 26 plus or minus. Start with what's easy. So k equals 1, meaning a factor of x minus 1. Alright, and then here we have 1, -8, 25, and -26. So down comes the 1, multiply, that makes a 1, add, that makes a -7, multiply, that makes a -7, add, and that makes a 18, multiply, that makes an 18, add, it's not going to make a 0, that's the important thing, it's going to be -8, but that's not really relevant. What's relevant is that it's not 0, so no. Alright, k equals -1, which means x plus 1 will be the factor in question. So -1, 1, -8, 25, 26. Down comes a 1. Multiply makes a -1. Add makes a -9. Multiply makes a 9. Add makes a, sorry, I said add makes a 34. Multiply makes a -34. Add does not make a 0. Doesn't matter what it is, but it's not 0 because it's -8. But not really relevant. No. Okay. So no on that. Alright, well, what if k equals 2? Meaning we're talking about a factor of x minus 2. So then we got a 2, 1, -8, 25, -26. So down comes a 1, multiply makes a 2, add them makes a -6, multiply makes a -12, add makes a 13, multiply makes a -26. Sorry, it makes a positive 26. Add them makes a 0, and that's a bingo. Yes. So, okay, so now that's an x squared, that's an x, that's a constant. Which means that x cubed minus 8x squared plus 25x minus 26 is equal to x minus 2 times x squared minus 6x. So this is the same, equal to x minus 2 times x squared minus 6x plus 13, and that equals, and if that's going to equal 0, that's going to mean two things. X minus 2 has to equal 0, which means x equals 2, or x squared minus 6x plus 13 equals 0. And in order to figure this out, we need to consider the quadratic formula with a equals 1, b equals -6, c equals 13, and that then is going to leave us with x equals 6 plus minus square root 36 minus 4ac. That's minus 4 times 13 is 52, and then divided by 2a, which is 6 plus minus square root of, so that's going to be -16 divided by 2, and that then is going to be 6 plus minus 4i divided by 2. Just barely reaching the end of our rope here, so that means it's equal to, we can factor out a 2, so that's going to be a 2 plus minus 2i, sorry, 3 plus or minus 2i, all divided by 2, those cancel, so I get 3 plus minus 2i. So then our zeros, or our solutions, or zeros, either way. Our solutions are x equals 2, x equals 3 plus 2i, or 3 minus 2i. Oops. So those are the solutions. Alright, now the very last task that we can be asked to do is a slight increase in difficulty on a task we could already do. So finding a formula, given zeros, and a point. Use the zeros to make make factors. Include an unknown coefficient, A. Solve for A using the given point. Example of something like this would be, let's say, we wanted to find a formula for a polynomial with real roots. Remember, roots is just another name for zeros. Of x equals, let's say, negative 1/2, 0, and 1, with another point given to us. In the past, it has typically been the y-intercept that's been given to us. But let's say that let's say that 2 comma f of 2 is equal to, let's say, 2 comma 6. Okay, so then this is the x, this is the y that we'll be using to find the missing a. Okay, so we've got x minus 1/2. Sorry. X equals negative 1/2, which means x plus 1/2 equals 0. So that's going to be one of our factors. X equals 0, so that means that x is going to be one of our factors. And then x equals 1, which means x minus 1 is going to be one of our factors. So these are the three factors. And you usually put the x first, so it doesn't get lost. So x times x plus 1/2 times x minus 1. So then, so far, what we know for f of x is that it is equal to some mystery a times x plus 1/2 times x minus 1. Now we use the point that was given to us, 2 comma 6, and we'll use that to solve for a. So 2 is going to be the x, 6 is going to be the y. So what that means then, is that 6 is going to equal mystery a times 2 times 2 plus 1/2 times 2 minus 1. So 6 is equal to a times 2. 2 plus 1/2 is 2.5, or in other words, 5/2. Times 2 minus 1 is 1. So those actually cancel, and what we get is 5 times a equals 6, so a equals 6 over 5. Which then gives us, as a polynomial, f of x is equal to 6 over 5 times x plus 1/2 times x minus 1. Alright, and that's going to now do it for this edition of Math 111. Join me next time for the next episode, and I'll see you then.